Okay, I'm the host. Hey everyone. Let's see. So, next class we will do some review, by the way, because we have a midterm on Monday. Any questions?
Will the midterm be open note?
Yeah. Did you see the study guide that I put out?
Well, now I have. I had never really got the time to do it until now.
Yeah, I put out a study guide, and it says that notes are allowed. Hang on, I'm a little bit concerned. Folks haven't been seeing my announcements because there's always like last minute technical difficulties. So I asked that people, like practice using their camera and their ID and such. It's kind of a pain to have to deal with that on the day of the test. Martha sent me a direct message that says, will the midterm cover all chapters we have gone over in class? Martha, did you see the study guide? Okay, yeah, so the study guide, it has the sections covered on it, and they are up to what we did on Monday, so including what we did on Monday. So what is that? The change of variables. So it's everything we've covered up to and including, what section is that? Is it 6.2, I think? Yeah, 6.2, I believe, on the change of variables. Okay, well, there's nothing else. We can start talking about vector fields all the way from back in chapter 4. So maybe in theory, this is something that you might have already learned like in the previous class, but the way that UCSD has the curriculum set up for 20C and 20E, we're supposed to cover this now. But it's a pretty important topic. I'll explain why in a second. So let me start with the definition. Okay, so what is a vector field? Well, a vector field is a map or a function from some subset of Rn back into Rn. Okay, so it takes in a vector and it spits out a vector. In that sense, it assigns a vector to each point in space, or at least to each point in its domain, which might not necessarily take up all of space. You can draw it, or at least attempt to try to visualize it by imagining that at each point in space, there's a vector attached. So this is something we're going to try to do today. Just imagine that at every point, there's some vector. Maybe it points to the right, or maybe it points to the left, or maybe, it points down, or maybe, it points whichever way. I obviously can't draw a vector at every point in space. The picture would be too messy if I did that. So often, in order to try and visualize what a vector field looks like, we'll just pick like a few select points. Often we will pick integer lattice points. And then at each point, we draw a vector. And sometimes we don't necessarily draw them to their full length because, again, the picture would get too messy if we did that. Usually it's sufficient if in our drawing of a vector field, we at least just indicate which direction the vectors are pointing. And maybe we can try and get the lengths correct as well. The first thing, the most important thing you want to indicate is which direction they're pointing, because often that will capture the qualitative behavior that we're interested in. Now, I said that vector fields were really important. The reason is that a lot of super important physical phenomena are vector fields. So gravity forms the gravitational field, right? At each point in space, you could draw a vector that gives the force of gravity at that point. Same with electric fields. Right now, electric fields are flowing through you, permeating you. Every single cell in your body has electric fields at every point pointing in some direction. Same with magnetic fields. Another example, which is a pretty cool one, is fluid velocity or fluid flow. So if you imagine, if you will, that you've got some river flowing, like a current that's flowing, and at each point in the river, you know the velocity of fluid that moves through that point. So that assigns a vector to each point in space, at least in the domain. So that's another example of a vector field, which I'll talk more about later on today. But contrast the idea of a vector field with that of a scalar field. So a scalar field just assigns a number to each point in space instead of a vector. Another way of saying that is that a scalar field is a map from some subset of Rn to R. So it assigns a number to each point in space, and important physical examples include temperature, or pressure, or potential energy, height, the distance from some point, density of, say, charge or mass or particle number. And scalar fields are also pretty important because, as we'll see, a lot of important vector fields come from scalar fields in some sense. Any questions so far? Okay, so a note about notation. If we're talking about a vector field in R3, for example, then this is what it might look like. It would have a first component. That's some function of x and y. And it would have a second component, which is also a function of x and y, and similarly for the third component, right? Because a vector valued function, it's really like a collection of three functions, or more generally, if we're talking about a vector field in Rn, then it's a vector of n functions. Also, just a heads up, if we have a vector field and each one of the components is k times continuously differentiable, that means for each one, you can take k partial derivatives with respect to any of the variables that it's a function of, and all of them are continuous. In that case, we'll say f is of class ck. And in this class, for the most part, in general, we'll assume that vector fields are at least C1. So we can at least take one partial derivative for the most part. Okay, so before I get into the problems, I need to talk some more about notation, particularly with respect to unit vectors. The position of a vector in space is often represented with its x, y, and z coordinates. And when we write this as a vector, sometimes I'll use the letter r a boldface R to represent the position vector, particularly in this context. So you're going to see that a lot. I thought I would just mention that you'll commonly see me and the textbook write that. So if we're using the letter R for your position, then the magnitude of R, that is to say, the magnitude of x, y, z, that is to say, the square root of x squared plus y squared plus z squared, this is your distance from the origin. And occasionally, we're not going to want to draw those vertical norm bars. So instead, we just don't write the bold anymore. Okay, so if bold R is this vector, then the non-bold R is the length of the vector. And yeah, Nikhil, in general, bold means vector in this class. When I'm drawing them by hand, I started trying to do them like that. Another common notation is to use little arrow symbols. I could be doing that as well. I don't really care which one I do, but I started writing them like this. So I guess for now I'll keep doing that unless anyone wants me to switch to arrows instead. It doesn't matter to me. But yeah, if R is the vector x, y, z. Oh, Kevin prefers vectors. I can do vectors, or arrows rather. I can do those too. So if R is the vector x, y, z, then R without the vector symbol would be the square root of x squared plus y squared plus z squared. Yeah, I actually like the arrows better myself as well. The reason I wasn't doing them was I was trying to make my handwritten work more in line with the printed text from my notes and from the book. But yeah, I'm totally fine with drawing little arrows as well too. Okay, yeah, that seems like some folks like the arrows. I'm with you. I can do that. Although when I'm writing them using formatting, like LaTeX formatting, as in my notes, they'll typically be bold, like what the book does. Okay, so as I think most of you know, I've mentioned it before, we say that something is a unit vector if it's a vector of length 1. And we often notate that with the little hat symbol. So what does it mean when you see a hat on top of a vector? Well, it means it's a unit vector, but it actually means even more than that. Because let's suppose that you have a vector that's not a unit vector. Well, this is our definition and convention. If you put a hat on a vector that's not a unit vector, what it means is the unit vector in the same direction. And I can give you the exact formula for that. So the unit vector in the direction of R is, you just take R and divide it by its length. So let me give a quick little example of that. So for example, how about if R is the vector 3, 4, 0? So the R lives in the xy plane. There's R right there. Then the unit vector that's in the direction of R would be, well, R divided by its length. The length of R, by the way, let me just write. would be the square root of 3 squared plus 4 squared plus 0 squared, which is 5. So the unit vector in the direction of r would be 1/5 of r, which is the same as the vector 3/5, 4/5, 0. And it would be about right there. Yeah. Okay, so that's a handy notation which we're going to make use of. Oh, and I mentioned the standard basis vectors. Notice we don't have to put the hat on the standard basis vector because they're already unit vectors. So it wouldn't be wrong. Like you could write I hat, and indeed, sometimes I will, and sometimes you will. It's totally fine to write I hat. It's the same as I because it's already a unit vector. So hats are okay. They're not hats is also okay when we're talking about the standard basis vector. Okay, so that's just setting things up so we can proceed. Let's do an example. How about of sketching a vector field? So let's sketch the vector field f of xy equals yx. In order to do so, I'm just going to choose some nice easy lattice points. Say 1, 2. And this can be kind of tedious in general, so I'll just go for as long as I can go for. Let's start with, how about f at 1, 1? Well, that's actually also the vector 1, 1. So I'm going to draw it like that. It goes over 1 and it goes up 1. How about f at 1, 0? That's 0, 1. So that one looks like that. How about f at 2, 0? That's 0, 2. So that one looks like that. F at, how about, let's say 0, 1 is 1, 0. Looks like that. Let's see, F at negative 1, 1 is 1, negative 1. That, that negative 1, 0 equals 0, negative 1. Looks like that. And okay, maybe you get the idea here. I'll fill in a few more of them. Okay, so I could obviously keep doing this for a while. I could also use software. So in this picture below, you can see the result of asking software to compute the vector field for me. So it drew the vectors for me. You can find a number of applets or programs or web pages where they'll plot these vector field plots for you. Can sometimes be useful for getting an idea of what they look like, but you should still be able to do them yourself. In this example, I also mentioned flow lines. Now, I haven't actually said what those are. So flow lines are the trajectories in which an object would be moving if it were in a velocity field described by your vector field. Like, I don't know, imagine that maybe there's a little sailboat. And it lived in this vector field. So It's being pushed or flowed with velocity pointing in the direction that the arrows are pointing. So the flow lines are the trajectories that this boat would follow. So let me see if I can guess some of them. It looks like, let's see, it'll be moving to the right and then up here. This is kind of informal. The idea with the flow lines is at each point, let's say at this point right here, your velocity is pointing in the direction that the vector field points in. So the flow lines will roughly look like that. That's a few sketched flow lines. Any questions on the vector field plot or the flow line? Okay. So let's talk about gradient fields. So first, let me remind you of what a gradient is. If you have a scalar valued function defined on a subset of R3, then its gradient is a vector whose components are each of the respective partial derivatives. So the gradient is a vector. Right? This quantity right here lives in R3. Thus, the gradient is a vector field. Yeah, I mean, it's a function where you stick in a vector, the location, and it spits out a vector. So gradients are vector fields. They're a special kind of vector field. Gradients are a particularly important and relevant type of vector field. We'll call them gradient fields. And as we'll see, a lot of the most important examples, for example, from physics, end up being gradient fields or gradient vector fields. Let me test you all. How about? So I just said something about how gradients are vector fields. Yes or no? If F is a vector field, then its divergence is a scalar field. Yes or no, folks? Let me just remind you what the heck del dot F is. So F, let's say, has components F1, F2, and F3. And del dot F, which is also sometimes written as div F, partial F1, partial X, plus partial F2, partial Y, plus partial F3, partial Z. Well, that's a scalar. It's a scalar, and it's also a function defined on space. So the answer is yes, this one is a scalar field. Any questions? Just see what, Roland? You have a question, or you were, or now you were just getting your answer into the yes or no question? Maybe there's some lag where Roland is. Probably just took the signal a long time to travel. Okay, so let's do another example. How about if f of x, y, z is the square root of x squared plus y squared plus z squared? The challenge is to show that the gradient is the same as the unit vector in the direction of the position. Oh, hold on, I need, okay, yeah. So I want to show this equation. Perhaps I should just start calculating the gradient of f. The gradient of f, I wrote the formula right up here. So I guess I need to take 3 partial derivatives. Let's just start with x and see what it looks like. So the first component of the gradient will be partial f partial x. That is partial x of this whole big square root expression. So this will end up being 1/2 times x squared plus y squared plus z squared to the negative 1/2, and then by the chain rule, I'll get a 2x. The 2's cancel. So I could write this as x over that whole big square root thing. Anyone recognize what the denominator here is? Another way to write the denominator?
Magnitude of r.
Yeah. And so yes, I could write that as magnitude of r. Or how about with my new notation, I say if you just write it like a scalar. So I could also write it like that. That's fine as well. Okay. So the other 2 components of the gradient are going to be similar. I'll just say similarly, partial f partial y is going to equal y over r, and partial f partial z will be z over r. So the gradient of f is x over r, y over r, z over r. I can factor the r out. And what's that? That's 1 over r times the vector r. But wait, that was our formula for the unit vector in the direction of r. Let me just draw this. Let's say that we're at some position, how about right here? And by the way, you can imagine there's a z-axis sticking out of the page. Sometimes it's easier to draw a 2-dimensional picture. So r points from the origin to the position. The length of that vector is r without the vector symbol. And when we took the gradient, we just got the unit vector that was pointing in the same direction. So there's the picture. The gradient of this function ended up just being a little unit vector pointing in the same direction. Is there something in the chat? Oh, sorry, I don't always see the chat when I'm lecturing. Let me see. Antoinette had a question. Can you explain the notation grad f in the first yes or no question? Is it the dot product? Oh, okay, yeah, sure. So yeah, let me talk about this for a minute. What the heck did I mean by grad f? So this del symbol, it's sometimes called del, or sometimes it's called grad, or sometimes it's called nabla, for those of you that know some LaTeX code. grad is not the best word because usually that refers to gradient. But del is pretty common. It's often called the del operator. And what is it? It's a vector of differential operators. So I don't know if any of you have heard about the concept of operators, but they act on functions and produce more functions. So taking a derivative is an operator. You can have a derivative operator. You stick a function in, it spits out the derivative. The del operator is as follows. Partial partial x, partial partial y, partial partial z. So you can operate on functions in different ways. If you operate with a dot product, that means you treat it like the dot product of vectors, except it's not a vector, it's an operator. All right, so from that notation, we get that the gradient of a scalar function is del f dx, df del f, or sorry, partial f partial x, partial f partial y, and partial f partial z. And if we operate on a vector function, then you use the dot product rules where like you apply, so that it's kind of like partial partial x, partial partial y, partial partial z, but dotted with f1, f2, f3, which is how we get partial f1 partial x plus partial f2 partial y, partial f3 partial z. Does that help, Antoinette? Cool. Yeah. Thank you for asking. I strongly encourage students to speak up if there's something that you're not sure about. So, okay, cool. So I finished this example. Any other questions, say, on this example here? This is a pretty typical example. It's a calculation that it's the type of calculation that you're going to be expected to be able to do. And in fact, there's another problem today that's similar. Yeah. Okay. Krishna says, how do you multiply F1? Okay. So it's not, it looks like multiplication, but it's not really multiplication. It's applying an operator. So arguably, this is just notation when we write a dot product, but with an operator. And what it means is you apply the derivative to the function as I did here. So you can just say that's what the notation means to answer your question, Krishna and Jose. Okay, so moving on to potentials. Suppose we have a vector field capital F, but it's equal to a gradient. In fact, because it's a convention, let's make it equal to the negative of a gradient. That's actually a physicist's convention, which is not particularly important for our purposes, but just to be consistent with physicists, I'll leave the negative sign in there. Anyway, when that's the case, and when capital F is like a force or an acceleration, well, then we often call V, the function that it's the gradient of, we call V the potential. And it usually has units of energy, or perhaps energy per unit mass or energy per unit charge. Potential energy, for example. So here's an example with that, and you might recognize this because I've mentioned the Coulomb potential before. So the Coulomb potential is V of r equals 1 over r, right? This is a scalar function equal to the inverse of your distance from the origin. Physically, it's the electrostatic potential energy of two unit charges that are a distance r apart. So let's say you've got one unit charge at the origin, and you got some other unit charge, say up here somewhere else, and they're a certain distance r apart. Well, then they have a certain energy, and the closer they are together, the more energy is required to push them that close. If they are like charges, then they repel each other. So they want to push each other away. Let's find the force that they push each other away with. And in doing so, by the way, we'll see why this minus sign is important. So let's do this calculation. V is 1 over r. F is negative grand V. What is F? Let's find the Coulomb force. So you should try this yourself, by the way. I mean, I'll do it right here, but you could just as well. It's the negative of the gradient of 1 over r. And you know what? Before I calculate that, let me give you a little fact about the chain rule, which you may or may not recall. So call the chain rule the 20C fact. How about if g is a function from Rn to R, and h is a function from R to R, then the gradient of h of g of R is equal to h prime of g of R times the gradient of g. So in order to use this fact, how about I call this function, let's say, h of r, i.e. h of r is 1 over r. So then, according to the chain rule that I just wrote down, we'll get negative. The derivative, by the way, oh, here, let me just do this calculation for the derivative. So h prime of r is negative 1 over r squared. So I'll get negative 1 over r squared times the gradient of r. If you're looking for an analogy with what I called g in this problem, g of, this is where the language is going to get kind of confusing. G of r is r, but without the bold. So g of the vector r is the length of r, if you're looking for an analogy with this formula. Okay, so I'm going to be impressed if anyone knows what this term is. You're paying attention. not 1, it's not 3, but it is something that we've talked about already today. To be really paying attention, but I just did this calculation actually. I just found what the gradient, yeah, that's the unit vector in the direction of r. So we just did this calculation. That was the last example. I'll show you right here. Yeah, we just found that the gradient of the length of r is the unit vector in the direction of r hat. Good. So that makes this calculation a little bit easier because I don't have to repeat that part of it. We get 1 over r squared times r hat. In other words, let's just cross on r. Here, let's say that this is 1 over r squared times r hat. Now, some of you may recognize this force. It's got a famous name called the inverse square law. So you've probably heard of the inverse square. Both gravity and the Coulomb force in electricity obey the same inverse square law. It's hugely important. It's got like massive physical consequences. It makes gravity and electrostatics almost comparable mathematically, like they're almost the same thing, except for the fact that there's no such thing as negative mass, but there is a such thing as negative charge. So mass always attracts. Unless maybe there's some like parallel universe where there's a such thing as negative mass, where mass pushes each other apart. But in this universe, we have not observed, or at least been able to actually see such a thing as negative mass, but you can have negative charge. Notice the sign of this term is positive, indicating that these charges are repelling each other, as we know like charges to do. Okay, so that wraps up this example. Any questions on this one? All right, so let's talk about flow. And this was one of the other examples of vector fields that I mentioned was for fluids. Fluids, by the way, include gases. Okay, like just because we say fluid flow, that doesn't mean it actually has to be a liquid. So gas behaves like a fluid. Let's suppose that we have a vector field, capital F, and it's the steady state velocity field of a flowing fluid. I use the word steady state. You might think, well, wait, if it's flowing, then it's not steady, is it? What a steady state means the velocity field is not changing in time. So it's kind of like you've got some flowing water. Okay, so there's a little boat right there, and the boat follows the flow of the stream. At each point, you have a certain velocity, and those velocities don't change. Although, if you actually like kept track of any particular particle of water, yes, that would be moving in time, but the velocities don't. So that's what we mean when we say steady state. Now let's look at a particular, say, particle of water in this velocity field, or perhaps a boat, if you will. So if I let boldface C or vector C of t be the position, like let's say of this boat, as it flows through the fluid, following the velocity field, that means it will be moving in time, and vector C will be its position. You may then remember from 20C that like if vector C is your position and C prime of t, is your velocity. Like derivative of position is velocity. Okay, so putting those two facts together, we get a very important equation in fluid mechanics and differential equations. It's the flow equation. So this is the flow equation. All it says is that if you keep track of some of the trajectory of some object that's moving in this fluid, well, the velocity of that object will be the velocity of the fluid. On the left side, we have the velocity of the object. On the right side, we have the fluid velocity evaluated at the position of the particle. So that all that equation says is this boat is moving with the same velocity as the fluid is moving at the same point. So it's almost like a tautology. Like, yes, of course this must be true. That's what we mean when we say the fluid velocity. Okay, so yeah, like I said, this equation comes up in differential equations all the time. So let's do one last example with that. How about by considering the vector field in the plane given by f of r equals x over r minus y over r plus x. And I already went through the trouble of plotting it. So there's a picture of this vector field or velocity field. Let's verify the flow equation for a particular trajectory given by vector c of t equals t cos t, t sine t. Verifying the flow equation means, well, checking to see if this equation is true. So let's see what the left-hand side is and see what the right-hand side is. The left-hand side is c prime of t. So that's going to be d dt of t cos t, t sine t. By definition, when you take the derivative of a vector, that's the derivative of each component. So that'll be cos t, t sine t, that's the derivative of the first component, and then sine t plus t cos t, that's the derivative of the second component. The right-hand side, this one, will then be, let's see, so that's, it's f of c of t. Now, c of t, let me say, like, this is the x component of c of t. And this is the y component of c of t. When I wrote little r right here, that's supposed to be the magnitude of the input. So here, r is the magnitude of r. So if we input the vector c, let's see what little r would be, or what scalar r, perhaps I should say, would be. Here, so let me just maybe do the calculation right here. So scalar r would be the square root of x squared plus y squared. The square root of t cos t squared plus c t sine t squared, then ends up just being t. So r is t on this trajectory. Okay, so I'm going to get, let's see, t cos t over t minus t sine t sine t over t plus t cos t. T's cancel. We get cos t minus t sine t plus t cos t. Is that the same as the left-hand side? There's the left-hand side. So yeah, they're the same. Hooray. And anyone know what these trajectories look like, by the way? Oh, I have an animation I can show you. Anyone want to guess before I show? A spiral. Yeah, here it is. So these lines spiraling out are the trajectories, as are the motions of these little balls or dots. Okay, so that's what the flow looks like. And we were looking at one of those trajectories in particular. So I go back to OneNote. Yeah. So anyway, that's what the trajectories look like. They just, or the particular trajectory rather, it starts at the origin and then it spirals out. That's what this trajectory looks like, and it is indeed a flow of the velocity field as we verify. Okay, so that's it, folks. Any questions?
Does this flow equation just means like it doesn't matter what kind of equation it is for the vector field, they are always equals to the c prime t?
No, in general, like most trajectories would not satisfy that equation. I had to choose a very specific one, which ended up being a solution of the flow equation.
Okay, so sometimes the flow equation doesn't stand, or it only works in some equation.
Yeah, so if this equation is not satisfied, then the trajectory that you inputted would not be a flow of that vector field.
Okay, can you explain that a little bit more?
Yeah, like what if you inputted, say, a trajectory that, I don't know, went like that? Well, that one is not following the vector field, right? They're supposed to be pointing in the same direction at each point. Here, one of them's pointing that way and one's pointing that way. So that would not be a flow and it would not satisfy the equation. A flow is an equation.
Thank you.
At each point, it's pointing in the same direction as the vector field. Okay, cool. Well, yeah, that's it, folks. I'll see you all Friday and hang out for office hours.
Hi, I have a question about the midterm.
Mhm.
So am I allowed to use the tablet to write down the answers?
Yeah.
Oh, okay, cool. Thank you.
Mhm.
Can you go back to the beginning of vector fields introductions? And I'm a little confused of like the CK and the C1. Does CK and C1, those just kind of stands for like how many dimensions they are in a vector field?
No, it stands for how many derivatives we can take.
How many derivatives?
Yeah, that's what the K means. It's how many times differentiable the function is.
Okay, thank you.
Mhm. So someone was asking for problem. 5.3 question 2B. Hold on a second.
Thank you, Professor.
Mhm. Okay, yeah. So Jose was asking about oh, my freaking mouse. Crap. Jose, do you have the problem on this on your screen? Okay, so you don't have it on your screen? All right.
I have my textbook open on my screen if you want me to share.
Okay, yeah, sure, go ahead. Yeah, I guess whoever can bring it up. Huh. All right, cool. So, Jose, what is, do you have an idea of how to start this? What's like maybe a first step?
Yeah, so what I did was I graphed the bounds for y and x.
Alright.
Yeah. But what I'm having trouble with is though like we can see that with the bounds for dy, it includes the negative region.
The negative region?
Yeah, like quadrant 4, I think.
Yeah, okay.
Yeah, so I don't know if that should be part of D, or is it just the positive regions or quadrant 1?
Okay, yeah, so there's where y is equal to x. There's where y is equal to negative x. And x goes from 0 up to 3. So the negative x is like the function on the bottom, and the positive is the function on the top.
Mhm.
So that tells you what the bottom and the top are. So this is on the bottom, and yeah, and this one's on top. So
Okay.
you got this region.
Oh, okay, I see. Yeah, I guess I was confused. Like, do we just count the region that's bounded to x? But it seems like it's both.
Sorry, I don't know if I heard that. What did you say?
Oh no, I was just confused because I was originally counting the region bounded between the x-axis and y equals x. Yeah.
Oh yeah.
Mhm.
Yeah,
Um,
right. This would be one of the differences between this and say like 20b, where in 20b a lot of regions are bounded by the x-axis, but yeah, in this class, no, they'll just be bounded by whatever function is on the bottom.
I see. Okay. And then so how about in the case of like 2a then, where you have the top function by equals square root of 4 minus x, but the bounds for y is from 2 to negative 2.
Okay. So y goes from negative 2 to 2. And x is, one of the bounds is 4 minus y squared. What's that look like anyway?
It looks like a parabola, but flipped.
Okay.
Yeah.
Which way does it open?
It goes from right to left, right.
Yeah. Okay. So if you plot the set of points where x is 4 minus y squared, it'll look like that.
Okay.
So that curve forms one of the boundaries of the region that you're interested in. Which side of the region? Is it like the top or the bottom or the left or the right or what?
It would take quadrant 1 and quadrant 4, right?
It involves those. Yeah, it has pieces in both of those.
Mm-hmm. So yeah, I think it's just the whole right section then.
So what's the, okay, yeah, and then what's the left boundary of the region?
0.
Okay, yeah, so there's this one. Okay, yeah, so then that leaves this one.
Okay, I see. All right, thank you so much.
Yeah.
I have another question from the book, so maybe we can leave it up. Oh, or no, we're back on the professor screen now. My question is 6.1, number 5.
Yeah. Yeah, this one is related to an example I did in class. I was talking about this transformation because standard polar coordinates transformation.
Yeah, so yeah, I think I understood that part. I was basically saying that like S star and S, they look the same. They're both like the unit disk without the origin.
S star is a product of two intervals. So one of the sets lives in the XY plane. Another one lives in like a different space. It lives in R theta space, which doesn't look like XY space. Let me show you the lecture where I was talking about this, because I drew a picture on that day, which is relevant. There.
Oh. So
Yeah,
in
when you
theta space, then it's a rectangle, and in XY space, it's a unit disk.
yeah, because I mean it is a product of intervals, which looks like a rectangle in that space.
Okay. That is not like my main part where I'm stuck though.
Okay.
Because I guess that doesn't really change what S is. My definition for S stays the same. So then I'm trying to show that T is 1-to-1 on S star. So I said, suppose T of R theta equals T of R prime theta prime. And I want to show that R equals R prime and theta equals theta prime.
All right.
So I started by like expanding what T of R theta means and what T of R prime theta means.
All right.
I got R cosine theta equals R prime cosine theta. I square both sides.
Wait, say what equation you got?
So I got R cosine theta equals R prime cosine theta prime.
Okay.
And I also got R sine theta equals R prime sine theta prime.
Cool.
So then I squared both equations and added them together.
All right.
And then I factored out the R squared. And so on the left, I had R squared times sine squared plus cosine squared. So it was just R squared on the left. And then on the right, I had R prime squared.
Cool.
So then I said R equals plus or minus the square root of R prime. But we know R is on the interval 0 to 1. So we can throw out the negative and we get R equals R prime.
Cool.
Now I am stuck trying to show that theta equals theta prime.
Now that we know that R is R prime, I guess I can ditch the little primes on the R's right here, right?
Yeah. So cosine theta equals cosine theta prime and sine theta equals sine theta prime.
How did you do that?
I divided both those equations by r.
And you're allowed to do that
Because-
exactly when?
I think now because r can't be equal to 0.
Oh, okay. Good. Yeah. So now maybe you see why it's important that we not be including 0.
Yeah.
If we did, then you could get like different angles corresponding to the same point, right?
Yeah, that's true. Yeah, if r is 0, you could put in any theta and get the same thing.
Yeah, okay, good. So because it's not 0, you can cancel the r's. And yeah, then you get, cos theta is cos theta prime. Sine theta is sine theta prime. Let's see, so like, here, so maybe we could just use like this equation. Cos theta is cos theta prime. How can that tell you that theta must equal theta prime?
I don't think it can. First, I thought it meant that theta equals theta prime plus 2k pi, but I don't think it means that either, because like cosine of like pi minus a tiny little bit is the same as cosine of pi plus that tiny little bit.
Yeah.
Oh, sorry, I'm in Alexander's right now. I'm in Alexander's right now. So yeah, I wasn't really sure where to go from cosine theta equals cosine theta prime. I believe that those two statements together mean that theta equals theta prime. I just don't know if there's like a trig identity to do it or what.
Let's see, let me think what like the best way to explain this would be. So like maybe let's look at the graph of sine. Here's the graph of sine, and one possibility is that theta equals theta prime, obviously. Another, let's say, is that if sine of theta is positive, so maybe theta is right here, what if theta prime was right there? In which case their signs would still be the same. Okay, so maybe you could just handle that case like, what if theta prime was pi minus theta? Can you like eliminate that as the other possibility?
What is the difference? Oh, it's it. Hang on. Okay, so theta, like in a drawing. In the drawing, doesn't seem like theta prime is pi minus theta. Or oh, that's pi there, right? It's pi over 2 in the middle. Okay. Yeah, so so I guess we can say, okay, from sine theta equals sine theta prime, that means theta prime equals pi minus theta, or then we have the negative one where theta prime would be um, 2 pi minus theta. Like if we were in like the negative part sign.
Oh, yeah. Okay, yeah. So if theta was somewhere in this region, I don't know, like maybe theta was there, then maybe theta prime would be, right there, which I guess is
Or that'd be pi plus 2 pi minus theta, which is
mhm.
3 pi minus theta.
Actually, let's see. Yeah, I guess so.
It's a weird equation, but okay. Okay, so that's, yeah, the first one was if 0 less than or equals theta less than or equal to pi, and the second one is pi less than theta less than or equal to 2 pi. Oh, yeah, it's just less than 2 pi because we can't be 2 pi.
Mhm.
Okay, and now we have to go into the cosine equation to show that those won't work.
Yeah, and you should get some contradiction.
And we have three options. We have the two we just discussed, and then the third option is or theta prime equals theta.
Yeah.
And then we just have to get a contradiction from the first two. Okay, let me work on that for a little bit.
All right. If anyone else has a question, go ahead.
Hi, I had a quick question on homework 5.5.
All right.
Let me share my screen. I think I figured it out, but I had a question about the way I solved it. So here's what I did. So I think they gave us most of the bounds for this question, number 13, but I had trouble with, I know that the bounds for z were 0 and then minus x minus y, but I had trouble figuring out if it was above or below, like z equals 0. So I tried to draw it out, but I don't know if you have any advice for like trying to draw things like this.
Yeah, how to Draw that. Sometimes I like doing like slices in the coordinate planes. Like you let y be 0. That gives you a line in the xz plane.
Yeah, so for here, I put like if x equals 0, then
Oh, yeah.
equals negative y, but I wasn't sure how to draw that.
So, okay, yeah, if x 0, negative 1. Like that.
Okay. And then it would be the same for negative x, just going
Mhm.
the opposite way. Oh,
Mhm.
okay. Okay, that makes sense. Yeah, because it's below z equals 0. Okay. Yeah, so does that look correct? Like the way I solved it?
What are you supposed to do?
Just find the integral, like for the volume of the region. But I just did all this work to try and figure out like whether the plane was above or below.
Yeah, that looks good.
Okay, and then I had a quick question about number 11 as well. So when you're trying to find the region bounded by two equations like this, you just find the intersection, right? To find the formulas for y.
Mhm.
Because I just set them equal to each other and then I got this formula. I figured this was like this oval in between them.
Yeah. This one, what's a little bit harder about this one is the two paraboloids don't have quite the same shape. One of them is kind of elliptical in its cross sections because of the. Wait a second. Hold on. Sorry, I take that back. X squared plus y squared. Okay, I think there's a oh, okay. I think there's a 2 that's supposed to be right there, right?
Let me check. This is problem 11. Oh, okay, yeah, there is.
Okay. So this is a paraboloid. And yeah, this one's an upside down paraboloid, but the second one is because of this 2, it kind of changes the shape a little bit. It makes it kind of oblong. Like still a paraboloid. But when the two of them intersect with each other, because let's say this. Because of the loss of symmetry, let's go with that. The intersection is actually going to, I think, look like this.
Okay.
It's not a big deal. I think that actually doesn't even really affect any of the calculations. It just slightly changes your picture here.
Oh, okay. So it just looks different than what I pictured.
Yeah,
But
they don't, yeah, it's not necessarily a disk. I think it's more like a poopy thingy.
okay.
A floppy disk. But yeah, other than that, I think like actually everything else is still the same.
Okay. So then I would just use this equation to find the bounds for y, like I did here.
Yeah. What's this shape called?
I forgot. It's not like a circle, it's like an oval,
Yeah, right. We call it an ellipse.
an ellipse. Yeah, that's the name.
And yeah, so you solved yeah, you solved it correctly. That's the way that you can found like the top piece and the bottom piece.
Okay, cool. All right. Those were my questions. Thank you.
Mhm.
I'm gonna finish solving the integral, so I'm just gonna stay in the room in case I have another question.